everyone, and welcome to CRAMsurg, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMsurg from the wonderful region of the Yorkshire and the Humber.
Perfect. Right, so let's get started. So we're going to carry on our guides on statistical test, and today we're going to talk about non-parametric ANOVA. But before that, we're doing a quick recap on what we discussed on our last session on non-parametric tests. Usual disclaimers: not a statistician, not an expert on stat software. And these are the various things that we talked about so far. Last time we did a massive recap of pretty much everything but Wilcoxon test. So today it seems only fair to give Mr. Wilcoxon a little bit of glory. So today we are continuing our journey that we started sort of in this area of the of this massive flowchart, and we're moving towards skewed continuous data. We rehearse this bit, and we're going to talk about this bit, that is to say, non-parametric ANOVA. And we'll do that with Genovi. So let's start with a very simple question. I guess that could go to Lydia. Sorry, let's do Maddie. Do you remember what Frank Wilcoxon used to do for a living?
I believe he was a chemist.
Perfect. That's correct. And Emily, apologies, I keep calling you Lydia. What issues was he finding with parametric tests?
The data he was working with had quite a few outliers.
Yes, absolutely. Absolutely. Why was that, do you think?
Because he was running chemical reactions, and the rate at which the reaction happened can be affected by multiple variables. And sometimes then a reaction can happen really quickly or really slowly as a result. His numbers were then a bit all over the place, so they weren't normally distributed.
Absolutely. You run think of the human body, for example, and think of an infection. If the human body wants a particular reaction related to the proliferation of a bacteria or a virus to slow down, what does it do? It just raises the temperature. And when the temperature raises, the bug just doesn't replicate at a pace that is as fast. But temperature can affect any chemical reaction, so does concentration of the elements of it, pressure, etc., etc. So the data that he was getting out of his experiments was, as you just said, completely all over the place. Now, Maddie, we mentioned the word outlier. What is an outlier?
So an outlier is an observation of something which deviates significantly from all the other things to the point where you might think it was generated by a completely different mechanism compared to the others.
Absolutely, yes. I believe this was Stephen Hawking's definition. And as you can see, this fantastic vignette explains it really well. It is about how abnormal an observation is in comparison to what you would expect it to be if it was part of the same group. It's basically just a weirdo of the situation. So, do you remember how we can define and visualize an outlier from a mathematical standpoint? And there's a hint on the screen. Whichever one of you wants to take it, I don't mind.
Well, since it's on the screen, it's you using a box plot is normally the easiest way, and an outlier is any data point that extends more than 1.5 times the interquartile range above the third quartile or below the first quartile.
Yes, correct. So you can see that anything that's above this point will be flagged as an outlier or below. And it's relatively easy to do, and it's very easy to do with Jamovi, as we now explored a couple of times. I might show you again later just to rehearse this. So Wilcoxon was dealing with these issues in his test results, and he just couldn't quite square it with the tests that he had available for himself, such as Students T and Fisher's ANOVA. And he came up with a different mathematical way of testing difference between groups of continuous variables. And he did this through ranking, like similarly to what we saw in Carl Pearson's and then Spearman and then Kendall's correlation. So we start with a parametric test and then we move towards a non-parametric test using ranking as a way of sort of normalizing the distribution, if you like. And he thought, well, most certainly someone has thought about this before, and this must be published somewhere. And he started doing these massive researches in his local library. You can imagine this was the 1945. Local libraries, sending letters to people, asking if they had any sort of well-defined and approved way of running tests using ranking methods on continuous variables. So basically a non-parametric equivalent of Students T or stuff like that. And he couldn't find a single thing. So he decided to write it up as a paper. And he sent it to Biometrics, thinking, surely someone has described it before, and the reviewers are going to send me back the references so I can look it up. And he sent it through. And actually, the reviews he's received were like, wow, we never saw this before. This is genius. So he ended up being published in Biometrics in 1945. If you dig deep, 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 you will find that some other people have described similar techniques before, but he's the first one that kind of popularized it. And he described two tests. And Emily, do you want to tell me which tests?
Sure. It was the Wilcoxon rank sum test and then the signed rank test.
Correct. And what's the difference between them?
The rank sum test is for unpaired samples, and the signed rank test is for paired samples.
Exactly. The rank sum test is also known as Mann-Whitney U, as we discussed last time. It's basically the same thing. Do me a favor. Can you give me an example of paired samples?
So something like blood pressure in a group of patients before and after treatment. So you've got the blood pressure from before the treatment, and then there's a corresponding blood pressure from after the treatment.
Absolutely spot on. That's exactly how it works. So in paired samples, each value in one set of variables has a corresponding value in the other one. And we've seen how there's two different versions of Students T, there's paired and unpaired. Independent samples one. So yeah, that's a very important concept to remember, and thank you for explaining it. So finally, one quick reminder, just because we're talking about non-parametric tests, and non-parametric tests are applicable to data that is not normally distributed. How do we test if our data is normally distributed, Maddie?
So it can be visually by making a chart, or as shown here, or simply by running this Shapiro-Wilks test on Jamovi, as you've shown us before.
Excellent. Very easy to remember as well. Huh? Excellent. So after all this chit-chat, we are now in a situation where we know how to run a non-parametric test in when we have two samples. But what if we have more than two samples? Well, we need to ask the help of Kruskal and Wallis. These are two American guys. They worked in the same university for a rather long time, and they described together what is the equivalent of ANOVA but for non-parametric distributions, and is also known as the Kruskal-Wallis test. Now, bonus question for Maddie. Do you remember who described the parametric ANOVA first?
Fisher?
Fisher, yes. Fisher in these lovely fields and studies on how to optimize agriculture. Perfect, fantastic. So we're going to run this now through an example using my usual data set. Just for whoever's not heard this before, as part of a project that was my dissertation, I collected data about papers that were advertised on the Twitter network by 6 publishing journals. And today we are going to find out if there's a difference in terms of number of retweets that those papers are getting based on the journal that is publishing them. And there's 6 publishing journals, so we'll have 6 bunches of continuous variables. So as usual, we'll fire up our overall data set in Jamovi. This is, you pretty much everyone on the call presumably have seen this by now. So very simple, we go on ANOVA. One-way ANOVA, Kruskal-Wallis, as very cleverly Jamovi suggests, use non-parametric. And we have dependent variables and grouping variable. So the dependent variable we said was going to be retweets. And the grouping variable would be journal title. Plain and simple. If you would like, you can also have pairwise comparisons. That is to say, you can have a comparison of each of the single groups in the grouping variable with each other. But generally speaking, yes, you could say, based on this test, that there is a statistically significant difference in terms of retweets that papers get based on the journal that publishes them or advertises them, which is the same one. We can also check, as we said, if our variable retweets is normally or not normally distributed. There you go. Suffolk test. And if you want, you could also have a box plot, which, you know, as you would expect, shows that the data is very much not normally distributed and is extremely skewed. So there's the vast majority of papers receive very, very little retweets, and a few receive just a ton because they somehow become incredibly popular or because their content gets picked up by media, and they just explode and become a little bit viral. But as you can see, it's only a very small minority, which makes this data very abnormally distributed. Right, I am going to stop here.
Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical questions.